Today we are diving deep into AI data governance. Here's what we'll be covering today. First, we'll be examining why traditional data governance struggles with AI workloads, focusing on the specific points of friction. Second, I'll detail a four-pillar strategic framework for AI-ready governance. For each pillar, I'll share specific technologies and approaches. Third, we'll analyze the build versus buy decision. This is one of the most critical architecture choices you can make, and we'll use the decision matrix to navigate. Fourth, I'll share six critical failure patterns that I have observed in production enterprise deployments. And finally, I'll provide a phased 12-month implementation roadmap to give you an actionable starting point. So let's begin. To build a new system, we must first understand the limitations of the old one. The challenges we face are not minor, they represent a systematic mismatch across four distinct areas. Number one, the volume and velocity crisis. The first issue is one of scale and speed. Traditional governance was designed for a different era, one of which was for batch oriented analytical workloads like daily data loads and weekly reports. Modern AI systems, in contrast, often demand real time inference and continuous training loops. A major bottleneck we see is in the access control. Many legacy systems rely on manual approval workflows, often managed through tickets that operate on a timescale of weeks. In AI development, this is a non-starter. Data scientists they need to iterate quickly, and access to data has to be in hours, not weeks, which is pretty essential for any progress. Finally, there is the challenge of raw scale. Governance tools that were architected for millions of structured rows can break down when faced with training data sets that involves billions of rows, especially when the data is unstructured text or imagery. Now, number two, the data quality collapse. The second area of mismatch is data quality. Traditional governance relies heavily on what we call schema first validation. This works well for unstructured relational databases, but it's largely ineffective for unstructured data, the documents, the images, and the audio that powers many of the most advanced AI models. Our static quality checks also become pretty insufficient. A rule that validates an email format, for example, cannot detect a distributional drift. This is a critical concept. If your live production data's statistical properties begin to shift away from your training data, your model's accuracy can silently degrade. Your static rules will not be able to catch this. Furthermore, a key challenge is that identifying sensitive information like PII in unstructured text is now a machine learning problem itself. You cannot write a simple SQL query to reliably find a PII in a free text document. You would need to use models such as, let's say, NER models just to make the data safe for other models to be able to train on. Number three is access control gaps. The third challenge is in the access control. Most legacy systems provide permissions at the table level. You either see the entire table or you see nothing. For AI workloads, that's not granular enough. We need row level controls, for instance, to segment data by geography. We need column level controls to automatically mask sensitive PII. And critically, traditional systems have no concept of separating training access from inference access. The data a person is allowed to use for a training job is and always should be fundamentally different from the live production data an application endpoint is allowed to query for a real time production. Number four is cost explosion. The fourth issue here is the cost. In traditional analytics, the primary cost driver was storage, which is relatively stable. In AI era, the primary cost driver is specialized compute. So GPU training instances can cost hundreds of dollars per hour, and inference costs scale with every single API call. Without a governance system designed to track this, organizations often experience significant budget overruns. In my experience, this is common in the first year AI implementation, largely because compute costs are pretty opaque and not attributed back to specific models or teams that are incurring them. To solve these challenges, an AI-ready governance system should be built on four strategic pillars. Pillar 1 is dynamic access control. This is, in my view, the most significant shift in thinking. The goal is to move from static RBAC, which is role-based access control, to dynamic ABAC, which is attribute-based access control. RBAC is a simple model. This person is a data scientist, give them access to the training database. ABAC is far more powerful. It's a real-time policy engine. It evaluates a set of attributes to make a decision. A policy in ABAC sounds like this. Grant access only if the user is a data scientist and is working on the approved fraud detection project and the data itself is classified as non-PII and the access context is model training. This pillar requires automated PII detection as a foundational capability. This shouldn't be a manual tagging process. It should be an automated pipeline that uses NER models to scan and classify data as it arrives. For technologies, you can look at vendor solutions like Azure Purview, Collabora, or Immuta as they are specifically designed for this kind of attribute-based access control. The pillar 2 is Lineage and Observability. This pillar is all about tracking the complete lifecycle of your data and models. You must be able to establish dataset to model version mapping. When an auditor or even an internal developer asks you what data was used to train production model version 1.3, you must be able to answer that immediately with specific database dataset versions. Pillar also includes drift monitoring. This means continuously running statistical tests to compare your live production data against your training data's profile. Common metrics include for this is KL divergence, which measures the difference between true probability distributions or PSI. This is how you catch model staleness before it actually impacts your business decisions. Key technologies here are MLflow, which is widely used for experimental tracking and as a model registry, and tools like Data Hub for data lineage and quality monitoring. The third pillar here is cost attribution. This pillar is all about financial governance, so we must move beyond project level budgets and implement per model cost attribution. Your teams need to know the specific training costs, inference cost, and storage costs for each model they have in production. This creates a crucial feedback loop, allowing data scientists to understand the financial impact of their architectural choices. This pillar also includes automated storage tiering. Data should be able to automatically classified and move between hot, warm, and cold storage based on the access patterns. This is often a straightforward way to achieve significant cost savings. For this, you can use tools like KubeCost if you're operating in Kubernetes environment, or leverage the native cloud cost management tools from your cloud provider. The fourth pillar is compliance automation. This final pillar is about shifting compliance from a reactive, periodic audit to an automated real-time enforcement. This is best achieved through a policy as code. Your compliance rules, for example, no model trained on data containing PII can be deployed to production, should be written in a declarative language. These policies are then executed as a real-time pre-deployment policy gates directly into your CI/CD pipeline. If a model fails the check, the deployment is automatically blocked. This also requires immutable audits for regulatory needs, which provides a non-repeatable proof of what happened, by whom, and when. The standard technologies for these are HashiCorp Sentinel, or more commonly Open Policy Agent. OPA allows you to define and enforce these policies as code across your technology stack. When you're ready to implement this framework, you face a fundamental architecture choice. Should you build, buy, or take a hybrid approach? The build in-house approach essentially generally makes sense for organizations with truly unique and complex compliance requirements that vendor solutions cannot meet. It's also a valid path if you have already made a massive long-term investment into a custom, let's say in-house data platform. However, a word of caution. This path requires a strong, dedicated platform engineering team. You should also expect a long timeline, typically 12 to 18 to 24 months to reach a mature production-ready state. If you go this route, you will likely build an open source foundations like Open Metadata, Data Hub. So please be ready for that amount of effort for over the course of the next 1 to 2 years. The second approach is the buy vendor solution approach. This is often the right choice for when your workflows are relatively standard and your primary driver is speed to market. For example, if you have an upcoming regulatory deadline, a vendor solution can get you compliant much faster. Common vendor options include Azure Purview and similar solutions from AWS and Google Cloud. The deployment timeline is much shorter, often measured in months. Again, the primary trade-offs here are, of course, the cost, the risk of vendor lock-in, and the fact that customization can be limited. The third approach is the hybrid approach. In my experience, this is often the most practical and common choice for large enterprises. With this strategy, you buy a core vendor platform, perhaps for the 80% of your needs and that are standard, like the data catalog, and then you build custom extensions for the 20% that is unique to your business, such as a bespoke A-back layer. A common pattern is using Azure Purview as a foundational catalog, but adding a custom A-back layer and integrating it with the open source tools like MLflow. This balances speed and customization with a typical timeline of 6 to 12 months and a more balanced cost profile. Let's talk about how to make a decision. So there are the few key criteria for making a decision. Number 1, compliance simplicity. Number 2, team capability and data scale. And number 3, budget. So if you have highly unique needs, then it will push you towards a build or hybrid approach. For team capability and data scale, you have to consider that do you have the engineering talent available to build and maintain a complex distributed system for next 2 to 2.5 years. And for the budget, it's important to look at the 3-year total cost of ownership, which is TCO, not just the year 1 license fee or development cost. Finally, please do not underestimate this as well. Now, change management is pretty important. This is often costs as much as the technology itself. You're fundamentally changing how your teams work. The second point is here, you must budget for training, both for your platform team and for your end users. The third point is integration with your existing data lakes, warehouses, and CI/CD tools can easily consume 30 to 50% of the implementation budget. And the fourth point, which contributes to the hidden cost, is that you must plan for ongoing governance operations. This is not a set it and forget it type of project. You will need a dedicated staff to manage the platform and evolve the policies as time progresses. I want to share 6 common failure patterns that I have seen multiple times in production over the years. Avoiding these will save you significant time, budget, and risk. The first pattern is the access bottleneck. This is what happens when governance is implemented as a purely manual ticketing system. Data scientists wait weeks for data and they get frustrated and inevitably build a shadow ID infrastructure to work around the system. This ungoverned shadow system then becomes your single biggest compliance and security risk. A robust solution here is the automated self-service access-based policy. The number two failure pattern is hidden training costs. This happens when teams spin up a large GPU instances for experiments without any visibility into the cost. The monthly cloud bill can be unexpectedly explode, and the AI initiative gets a reputation for being a cost center. The way to address is that you have to go with the per model cost attribution, which we covered in Pillar 3 earlier. The third failure pattern is the compliance. This is a scenario where a model is deployed into production. 6 months later, an audit discovers that a sensitive PII was present in the training data. Now you have a regulatory crisis and you face potential fines and you must shut down the model immediately. The solution is that you have to have automated PII scanning gates before your training even begins. Pattern 4 is model staleness. A model is deployed and it works well, but the world changes and its accuracy is silently degraded because no one is monitoring for data drift. Your business is now making critical decisions based on unreliable predictions. This is why automated drift detection and retraining workflows from Pillar 2 that we just covered are so important. The fifth failure pattern is the lineage black hole. This is when an auditor asks you, can you reproduce this model's results? Or they can ask you something like, which data was used to train this? And the answer is sometimes we don't know, which is not good at all. You cannot debug production issues effectively in this case and you will fail audits. The solution here is to have end-to-end lineage tracking implemented from day one. The pattern number 6 is cross-environmental leak. This is a subtle but very serious security breach where development models are inadvertently trained on live sensitive production data. That not only causes model overfitting, but most importantly, it leaks that sensitive information into a less secure environment. The solution is to have strict environment access controls enforced by your ABAC system. And here's a 12-month implementation plan. It's a phased implementation plan to deliver quick wins and show value early while you build towards a full automated vision. The first phase, which is for first and second months, is for foundation and visibility. The goal of this first phase is to have immediate visibility and risk reduction. First, you have to implement the cost visibility dashboards. Even if they are just per team to start, this has to be done and it's a huge one. Second, you have to deploy automated PII scanning for all new training datasets. Third, you have to start with basic lineage tracking, focusing on the simple data set to model mapping at least. Fourth, you have to establish storage tiering policies to get some quick cost wins as well. The outcome here is that by end of this phase, you should have basic cost visibility and have mitigated your single largest compliance risk. The second phase is for core platform and self-service, and this is ideally should take between 3 to 6 months. This phase focuses on building the core enforcement agent. The high priority item here is to implement your dynamic ABAC access controls. This is a heavy lift here. Next, you should integrate your model registry, for example like MLflow, with the governance system. You will also establish the immutable audit trail infrastructure here as well. And finally, you will be implementing your first policy as a code enforcement gates as part of your CI/CD pipeline. The ideal outcome here is that you achieve true self-service data access. The manual approval workload for your team should drop significantly after this phase. The third phase here is the full automation and optimization part, which should roughly take from month number 7 to month number 12. The final phase is about the maturing the platform and making it more proactive. This is where you implement real-time policy information for any streaming data. You will also expand to cross-platform governance if you operate in a multi-cloud or a hybrid environment. And you will also be implementing full drift detection automation with retraining triggers. The ideal outcome here is that you should be having a fully automated, proactive governance system that manages the model lifecycle, risk, and cost with minimal human intervention. And here are some critical success factors. Across all these 3 phases, there are few factors that in my experience are critical for success. Number 1, the biggest one is the executive sponsorship. It's essential to secure sponsorship at the VP or C level. This is a cross-functional initiative that will require alignment from legal, security, and engineering. Number 2 is cross-functional governance council. You should establish this on day one. It must include leaders from legal, security, ML engineering, and data engineering. This council meets regularly to review policies and align on priorities. The number three is incentive alignment. This is a subtle but vital point as well. Your team's objectives should be balanced. If you only incentivize deployment velocity, you will get compliance shortcuts. If you only encourage compliance, then you will get stagnation. You must measure and reward both. For technology stacks, you'll see common patterns. Microsoft centric stack would likely use Purview, Azure Policy, and Azure ML. A multi cloud stack might use Collabora, Open Policy Agent, and ML Flow. Today, we examined why traditional governance models fall short for AI. We walked through the four pillar framework of dynamic access, lineage, cause attribution, and compliance automation. We analyzed the build versus buy decision, reviewed the six most critical failure patterns, and laid out a 12-month implementation plan. AI workloads requires a governance system that is designed for its unique speed, scale, and risk. By building this framework, you must move governance from being a compliance bottleneck to being a strategic enabler for scaling AI responsibly and capturing its full business value. Thank you for watching today. If you have any questions, please let me know. Thank you so much.